We know what the universe is made of. At least, we believe we do, with the particular confidence of a species that has spent 4 centuries building instruments to interrogate matter at increasingly smaller scales. Atoms, then protons and neutrons, then quarks and leptons, then the quantum fields that underlie all of it. The Standard Model of particle physics is the most precisely tested theory in the history of science. Its predictions match experimental results to more than 10 decimal places. We have found every particle it predicted, including the Higgs boson, discovered in 2012 after a 40-year search. The universe, according to our best and most rigorously tested understanding, is a physical place. It is made of real things. It exists independently of observation. It has no author. It follows no script. It was not designed. These are not philosophical preferences. They are the working assumptions of every laboratory, every observatory, and every physics textbook on Earth. They are the foundation beneath the foundation, and they have held more or less for as long as modern science has existed. And then there is the pixel. Not a literal pixel, not a square of color on a screen, but something far more disturbing, a fundamental, irreducible unit of reality, a smallest possible thing beneath which nothing exists and nothing can exist. Because if the universe is truly continuous, if space and time flow smoothly and infinitely at every scale, then there should be no smallest unit of anything. You should be able to zoom into matter forever, finding smaller and smaller structure without end. But you cannot. Physics has found the floor. The Planck length, approximately 1/616 times 10 to the power of -35 meters, represents the smallest scale at which the concept of distance retains any physical meaning. Below this scale, space-time itself dissolves into quantum foam, a seething structure of uncertainty, so violent that our equations break down completely and produce only nonsense. The Planck time, approximately 5 times 10 to the -44 seconds, represents the smallest meaningful interval of time. Below it, the concept of sequence, of before and after, loses all physical validity. The universe has a resolution limit, and a universe with a resolution limit looks, with uncomfortable precision, like a universe that was rendered. The first reason this matters is what physicists call quantization. Everything in the universe comes in discrete packets. Energy does not flow continuously. It exists in quanta, indivisible units that cannot be subdivided further. Light arrives not as a smooth wave, but as individual photons. Angular momentum is quantized. Electric charge is quantized. Every fundamental property of every particle in the universe exists in discrete steps, never in the smooth, continuous values you would expect from an analog physical reality. A universe built from scratch by a physicist designing a real place would have no reason to be quantized. Quantization is what you get when you discretize a simulation to save processing power. It is the signature of a system that was designed to appear continuous but is in fact composed of discrete computational steps underneath. The second reason is the speed of light. We treat the speed of light as a physical constant, the maximum velocity at which information can travel through the universe. But there is another way to interpret it. In any computational system, there is a maximum rate at which information can be processed and transmitted. This is determined by the underlying hardware. The speed of light in a simulated universe would not be a property of space. It would be a property of the processor. It would be the clock speed of reality, the maximum rate at which the simulation updates its state. The fact that the speed of light is not merely fast but is an absolute unbreakable limit on all information transfer, a limit that appears built into the structure of space-time itself rather than being a property of any particular medium, is precisely what you would expect if the speed of light were a computational constraint rather than a physical one. The third reason is the observer effect. Quantum mechanics contains within it a discovery so strange that its implications have never been fully absorbed by physics or philosophy. A quantum system does not have a definite state until it is measured. An electron does not have a definite position, a definite momentum, or a definite spin until an observation forces it to resolve into one specific value. Before measurement, it exists in a superposition of all possible states simultaneously. This is not a limitation of our instruments. It is not that the electron has a definite state and we simply cannot see it without disturbing it. Experiments testing Bell's inequalities have definitively ruled this out. The electron genuinely has no definite state until observed. Reality, at its most fundamental level, is indeterminate until something looks at it. A physical universe has no reason to behave this way. An observer should be irrelevant to the state of matter. But a simulated universe has every reason to behave exactly this way. A well-optimized simulation does not render what is not being observed. It holds unobserved regions in a state of calculated probability, resolving them into definite states only when an observer requires the information. The quantum mechanical observer effect is not a curiosity. It is a description of lazy evaluation in computational systems, a standard optimization technique in which calculations are deferred until their results are actually needed. The fourth reason is the mathematical structure of physical law. Eugene Wigner, one of the great physicists of the 20th century, wrote an essay in 1960 titled "The Unreasonable Effectiveness of Mathematics in the Natural Sciences." His point was simple and has never been adequately answered. Mathematics is a purely abstract system invented by human minds with no necessary connection to physical reality. And yet the universe appears to be written in mathematics with a precision and depth that goes far beyond anything required for human survival or even human curiosity. The equations of general relativity, developed by Einstein as a purely theoretical exercise, turned out to describe the behavior of black holes, gravitational waves, and the expansion of the universe with perfect accuracy before any of these phenomena were observed. The mathematics of quantum field theory predicts experimental results to 12 decimal places. This does not happen in a physical universe by accident. Mathematics should be an approximation, a useful map that resembles the territory without being the territory. But in our universe, mathematics does not resemble physical law. Mathematics is physical law. The universe does not merely follow mathematical rules. It appears to be mathematics, executed. This is precisely what you would expect if physical reality were a computational process running on a mathematical substrate. The fifth reason is fine-tuning. The fundamental constants of the universe, the strength of gravity, the mass of the electron, the cosmological constant governing the expansion of space, the ratio of electromagnetic force to gravitational force, are set to values so precise that the slightest deviation in any of them would produce a universe incapable of supporting complex structure of any kind. If gravity were slightly stronger, stars would collapse before producing heavy elements. If the cosmological constant were slightly larger, the universe would have expanded too fast for galaxies to form. The range of values compatible with a universe containing atoms, stars, planets, and life is extraordinarily narrow compared to the range of values these constants could theoretically take. Physicists estimate that some constants are fine-tuned to 1 part in 10 to the power of 120. The mainstream response to this is the multiverse, the idea that all possible values of these constants are realized in an infinite ensemble of universes, and we simply find ourselves in one compatible with our existence. But the multiverse is not an explanation. It is a mathematical framework that currently has no observational support whatsoever. An alternative explanation that requires no new physics and no unobservable entities is that the constants were set, that the universe was initialized with parameters chosen to produce the desired outcome. The sixth reason is information theory. John Archibald Wheeler, one of the most important physicists of the 20th century and the man who coined the term black hole, spent the last decades of his career developing a framework he called it from bit. His proposal was that physical reality, all of it, every particle, every field, every interaction, is fundamentally informational in nature. Not that information describes reality, but that information is reality. That at the deepest level, the universe is not made of matter and energy, but of binary choices, of yes and no, of 1 and 0, resolved by observation into the appearance of a physical world. This is not metaphor. Wheeler believed it was the literal structure of existence, and the mathematics of quantum mechanics supports it. Every quantum measurement is a binary choice resolved by observation. The universe, at its foundation, processes information. It does not merely contain information. It is information being processed. The seventh reason is entropy and the arrow of time. The laws of physics, with one minor exception, are time-symmetric. They work equally well run forward or backward. There is no equation in fundamental physics that distinguishes the past from the future, and yet time has a direction. Entropy increases. things fall apart. The arrow of time is real and universal and completely unexplained by the laws that govern every process within it. The standard explanation is that the universe began in an extraordinarily low entropy state and has been moving toward higher entropy ever since. But this explanation simply relocates the problem. Why did the universe begin in a low entropy state? The probability of any given configuration of matter having the extraordinarily low entropy of the early universe is almost exactly zero. A simulated universe would begin in a low entropy state for the same reason that a video game begins in an ordered state. Because someone initialized it that way. The arrow of time is not a property of physical law. It is a property of initial conditions. And initial conditions are set by whoever starts the program. The eighth reason is the holographic principle. In the 1990s, physicists Gerard 't Hooft and Leonard Susskind developed a framework suggesting that the information content of a region of space is not proportional to its volume, but to its surface area. Everything that happens inside a region of space can be completely described by information encoded on its two-dimensional boundary. This is called the holographic principle, and it has since been given rigorous mathematical foundation through the ADS/CFT correspondence, one of the most studied frameworks in modern theoretical physics. What the holographic principle implies is that the three-dimensional universe we inhabit may not be fundamental. It may be a projection, a three-dimensional rendering generated from a two-dimensional informational substrate. We may be living inside the projection of a lower dimensional reality, experiencing depth and volume as emergent properties of a system that at its foundation is flat. This is not poetry. It is the working framework of a significant portion of theoretical physics, and it describes, with uncomfortable accuracy, the relationship between a rendered environment and the data structure that generates it. The ninth reason is the simulation argument itself. In 2003, philosopher Nick Bostrom published a paper presenting what is now called the simulation argument. Its logic is simple and has not been refuted. It states that at least one of three things must be true. Either virtually all civilizations at our level of development go extinct before reaching the computational capacity to run detailed simulations of conscious minds, or virtually all civilizations that do reach that capacity choose not to run such simulations. Or we are almost certainly living in a simulation right now. The third option is not the conclusion of the argument. It is the logical remainder after the first two options are considered. If any civilization anywhere in the history of the universe has ever reached the computational capacity to run realistic simulations of conscious minds, and if that civilization ran even a modest number of such simulations, then the number of simulated minds vastly outnumbers the number of biological minds. In that case, a randomly selected conscious entity is far more likely to be simulated than biological. The mathematics of this argument are straightforward. Its assumptions are modest, and it has no clean refutation. The 10th reason is cosmic ray anomalies and lattice structure. In 2012, a team of physicists at the University of Bonn, led by Silas Bean, published a paper examining whether the universe shows signs of being a lattice simulation, a computational structure in which space is divided into a discrete, three-dimensional grid rather than being truly continuous. Their analysis found a specific and measurable signature that such a simulation would produce, a limitation on the energy of cosmic rays arriving from certain directions related to the lattice spacing, and they found that the observed spectrum of ultra-high energy cosmic rays does show an anomalous cutoff at exactly the energy scale predicted by this model. The result is not conclusive. It is consistent with other explanations, but it is also consistent with the universe having a lattice structure at the Planck scale, precisely the signature you would expect from a discretized computational substrate. The 11th reason is the problem of consciousness. Physics can describe the behavior of every particle in the brain. It can map every electrochemical signal, every synaptic firing, every neural correlation of experience. What it cannot do, and what no physical theory has ever done or currently shows any promise of doing, is explain why any of this produces subjective experience. Why is there something it is like to be you? Why does the processing of information in a physical system give rise to the inner experience of color, sound, pain, Joy. This is called the hard problem of consciousness, and it has no solution within the framework of materialist physics. Every proposed solution either dissolves the problem by denying that subjective experience is real, which contradicts the most direct evidence any of us has about anything, or relocates it without explaining it. In a simulated universe, consciousness is not a problem. Consciousness is the point. The simulation exists to generate experience. The hard problem of consciousness is not a bug in the simulation hypothesis. It is evidence for it. The 12th reason is the most personal and the most terrifying. It is the reason that physicists who take this seriously tend to go quiet when they reach it. Every physical law, every constant, every rule that governs the behavior of matter and energy in this universe is contingent. There is no logical necessity for gravity to follow an inverse square law. There is no mathematical reason the electron must have the mass it has. There is no physical principle that required the speed of light to be what it is, rather than 10 times faster or 1,000 times slower. These values are not derived from deeper principles. They are simply what they are. In a genuinely physical universe, this is a mystery without resolution. Constants are constants because they are constants. But in a simulated universe, constants are parameters. They were chosen. They were entered into a configuration file before the simulation began. And if they were chosen by someone or something with the ability to choose differently. The universe we inhabit is not the only possible universe. It is one specific configuration among an uncountable number of alternatives. And it was initialized with these specific parameters for reasons we cannot access and may never understand. We built science to describe reality. We built mathematics to model it. We built particle accelerators to interrogate it at the smallest scales we can reach. And what we have found at every level of investigation, at every scale from the Planck length to the observable horizon, is a universe that processes information, that quantizes its fundamental properties, that refuses to resolve into definite states until observed, that encodes its three-dimensional content on two-dimensional boundaries, that operates under parameters set to values of impossible precision, and that produces conscious experience through mechanisms that no physical theory can explain. We built the instruments to find the bedrock of reality. And instead of bedrock, we found something that looks, in the cold light of what we actually know, less like a physical place and more like a program running on hardware we will never be permitted to see. The universe may be real in every sense that matters to us. Our experiences may be genuine. Our relationships, our suffering, our love, our curiosity may be completely authentic. But authentic and physical are not the same thing. And the quietest, most unsettling possibility that modern physics has ever produced is not that the universe is vast or cold or indifferent. It is that the universe is exactly as detailed as it needs to be, exactly as consistent as it was designed to be. And that's somewhere beyond the boundary of everything we can observe or measure or even theoretically reach. Something is running a process, and we are what the process is for, and we will never know why. And the question itself may not be one that has an answer we are capable of receiving.